So let's talk about let's talk about the nanocomposite coatings. So we realize a composite material within nanometric particles are dispersed inside an amorphous phase matrix. So this is our phase matrix. And we have a dispersion of nanometric particles like this one. So let me write. On this, we realize a composite material with a nanometric particles dispersed inside an amorphous phase matrix So typically we have crystalline particles inside an amorphous matrix. For example, so these are the systems which can represent the nanocomposites. So why an amorphous matrix is preferred? So because in this type of system, we have large interface area. So in order to create this type of structure, we need a small interface energy. An amorphous matrix is able to reduce the mismatch energy between the different structure of the particle and the matrix. So usually it is difficult to combine two crystalline structures, and we can have large mismatch in the crystalline arrangement with a relatively large interface energy. Titanium aluminum nitride is an exception case, so the amorphous matrix is able to accept different structure with lower interface energy. So with this type of structure, we are able to achieve high hardness, which is around 50 gigapascal. And can be obtained in this type of composite material like this one. So how is it possible to generate this type of a structure, and what is the deposition process which is able to generate this type of structure? So typically we exploit the reactive process So the metallic elements are available in the target material. So in this case, nitrogen or carbon are delivered through the gas phase. So we have a reactive process with a proper composition of our target material. So the metallic elements are given by the target and the reactive elements are given by the gas. All these elements are collected in the growing films. Through proper selection of overall composition, we generate a system which is able to spontaneously separate the crystalline particle we desire. Then we create a two-phase structure during the growth. The structure is derived from the spontaneous precipitation and is able to so the metallic elements are given by target and the reactive elements are given by the gas. So all these elements are collected in the growing films. So through proper selection of overall composition, we generate a system which is able to spontaneously separate the crystalline particle we desire, and then we create a two-phase structure during the growth. So the structure is derived from spontaneous precipitation and is stable up to high temperatures, which is around 1000 degrees Celsius. So this is the metastable structure. So because of the small nanocrystal sizes represented here, which is diameters is around 3 to 5, diameters of these nanoparticles are around 3 to 5 nanometers, dislocation glide is made difficult and the extension of existing flaws is probably restricted to a few nanometer crack length, and crack length is small. Conventional fracture mechanics can explain the resistance to crack formation exhibited by these coatings. So the crack propagation is easy in matrix, and this coating offers good crack propagation resistance.